Hey yo, I'm gonna demonstrate how this two's complement works. We all know that a minus value will be represented in two's complement. The way is all the bit of the corresponding positive number will be inverted and then finally add 1. Because the highest, the most significant bit is the sign bit. If it goes to 1, which means it's negative. I want to find out the detail and how it works in memory. So that's why I write a program to find out, and using GDB to show how it works in memory. Tools complement demo. I'll go standard IO. First of all, I'll define a byte 5, and then another byte is -3, and then the value is a plus b, which should be 2. Then we print it out. So we use GCC, and then -g means with debug information. Output demo and then the program, and it compile. Let's run it. It's 2. Yes, the result is correct. So how does it work in the memory? I'm going to open it, use GDB demo, and be quiet. Okay, first step is I'm going to set a breakpoint at main. We see that in the first instruction there's a B plus here. Convenient, eh? And then we run, so it break, and then we can run the next line. Now A has value. We can use print. P means print, and then /t is display as binary format A, which is 101. Let's run the next. Now B has value. B is okay, that's a complement. That's a complement of 3. Why? We can prove it. If we print out 3, so we print out this one, it will be 1 1. So 1 1 is the binary format of 3. So according to two's complement algorithm, this will be all inverted. The byte in this cat type, which is 8 bits, all inverted correspondingly, which means this 2-bit, lowest 2-bit, will become 0 0, right? And then the remaining higher 6-bit will become 1 1 2 3 4 5 6, right? And then the last step is +1, which means this will be 1. This is exactly this one. So this proves this is a two's complement. So next, let's check out the result. We run it. We print the result. It's 1 0, which is 2, which is correct. We can just find out how it works. We can print 5 is 101. Print -3 is this value. And let's do it by hand. We start from the least significant bit, which is this one, plus this one, which end up 0, right? And then carry 1 to here. And the second bit, 0 plus 0, and then plus this carried 1, which is 1. And the third bit, 1 plus 1, end up carry 1, and then 0 here. And the 4 bit, here is 0, plus 1, end up 0 here, and then carry 1. And so on and so forth for all the upper bits, the more significant bits, which end up all these positions are 0. Except the last bit go out to 1, but it's out of bound. It goes to the 9 bit, so it will be dropped. So it end up 1 0. So it's perfect. The 2's complement is very, very easy. We can just use the normal rule for the binary addition. So I think at this point, I think I'm good enough to, in terms of the 2's complement, why it's used this way. I'm glad I learned something. I hope you also learned something. See you next time. Cheers.